We'll get started in 1 minute. Great. Hey everyone, welcome back from lunch. My name is Greta and I'm excited to introduce the BrainScore benchmarking competition. BrainScore is a platform to test on how well computational models perform on both behavioral and also neural data, neural recordings, also called benchmarks. So this competition is about neural benchmarks, the data that the models are usually tested on. So BrainScore, the first code for BrainScore is written in 2017, and a lot has happened since then, including a competition designed to find better models in 2022. And now things have been switched around a bit, and this competition has been about finding benchmarks that can help test these models as to how good they actually are of neural and behavioral responses. So I'll introduce Martin Schrimpf and Kokar, who are the main organizers of this workshop, and please go ahead and start your introduction.
Thank you, Greta. Thank you also to Ev and Talia and the whole CCN committee. This is great. This really feels like a home conference for us. And yeah, I'll have more thanks later, but I thought we would start by just declaring that our goal is to build a model of the system. Basically, how is it that the human brain gives rise to intelligent behavior? And personally, I think there's sort of three main underlying reasons for that. One is the basic science reason. We want to have a mechanistic understanding, a computational understanding of how intelligence actually comes about, how it works. It might lead to next generation AI. And finally, it might also lead to future applications that maybe can actually help people at some point. So if we now think about how to build such a model, then how do we build a model of a complex system? Well, I think there's one field that's pretty close to ours, which is AI. And usually there's sort of, at least two, maybe three things that come to mind in the AI. I would say one, of course, is compute, which I'm not going to go into detail here. But the other one is data. Probably everyone knows ImageNet. At some point, once we had 1 million images to actually train models on, and maybe importantly, then also another couple 10K to actually test them on, we were able to make a lot of progress. And this may be one version of what progress looks like. So on the x-axis, you see the different years. And on the y-axis is basically how the model accuracy over the years just became better and better and better. Basically starting pre-DeepNet area into AlexNet, into ResNet, and so forth. And one thing I want to highlight here is that these models built a lot on each other. Basically, machine learning was really good at sharing things and reusing things and recombining things. So once AlexNet came out, people used those components and improved them and shared them again. And then the community saw which of those components actually work out and which ones don't. And then you take the stuff that works out, combine it with maybe new ideas, and that's how you can keep building more and more of these things. And that, I would say in neuroscience, we've started to build and test models as well, but I would say we haven't really been as good at sharing and maybe recombining things. And that's one thing that BrainScore is trying to push for with a lot of open source and also open evaluation so that you can really directly see which of the models and which of the model components improve on things and which ones maybe don't. So you can see positive gradient towards, ideally, a complete model of the brain at some point. And so in a lot of ways, we are in a really good time because we have a lot of data. So this plot is about neural data, but there's also a lot of behavioral data. This is from the Stevenson lab. On the x-axis, again, are years. And on the y-axis, on a log scale now, are how many neurons you can simultaneously record. Each dot is just one experiment. So this goes up exponentially. Maybe it's even growing a lot faster now. But clearly, we have access to unprecedented amounts of data that we have never had before. And still, I would say it's been really difficult to make sense of all of this data. We don't really have ways to process all of this if we just go to the basement and think really hard. I would say rather there is a need for models here. We have to digest all of this, especially if you then consider maybe not just one experiment, but actually all of them together. Then really, I think there's just not a way around models. So maybe connecting to what Greta said in the beginning about where this all came from, sort of the earliest days were pre-benchmarks in neuroscience. And maybe as a quick shout out to my advisor, Jim, who's sitting in the front. I think when I started in the lab, one of the first questions I asked him was, I want to build some cool models. How do I actually test them? What are the standard benchmarks that I can test them on? And at the time, the answer was, well, we don't really have any of that. We have maybe data, but you can't really compare things. And especially if you want to compare with maybe models that are tested on other data, then really all hell breaks loose. So the first, initially it was really just code for a single project, and then eventually people found it useful. So at some point we start branching out from really these small-scale data to eventually put things together. Because otherwise you run into this case where you have what we call piecewise efforts. So you might have one lab that collects data from, let's say, V1 in the brain, and maybe they even build a model, and then that is published and usually discarded. And then there's another lab that collects data from somewhere else. Again, data is collected, model is built, publish, and discard. And then you're left with this sort of zoo of data and zoo of models that just don't really talk to one another. And I think in this case, it just seems like the sum of all these parts is much less than it could be. So you might know this Indian proverb where different people feel parts of an elephant. Nobody can really get the full picture. That's what we thought we were starting from. This is all, of course, necessary. You need this exploration in science as well, where you maybe don't yet put things together. But the view of BrainScore as a platform is really that it is the right time to actually scale things up and start integrating. So the hope is that we can build these system models that then are tested on not just one data set, but ideally all the data, and ideally also in an easy way so that we can really see the full picture. And so when we first started this, I tried to look at the first slide I ever presented this. This is from 2018. I had built a very pretty logo, which nobody liked, so then we had some revamping of that. But at the time, we just started from some data that we had lying around. You can see we didn't even have V1 or V2. So this was already a first need for integration, because then Tony Morfson's lab came in, gave us that data. And now there's, of course, a lot more efforts like Algonauts, now last year powered by the large-scale dataset NSD. There was, before all of this, Jack Allen's Neural Prediction Challenge, the neural latency benchmarks, and so on. I'm sure there's many others that I'm not putting here. So I think it's really starting to happen in our field, which I find very exciting. And we recently tried to then phrase this together, like why do we actually find this exciting? For me, it's mostly that I hope that these really good models at the end of the day will enable new technologies, new applications. And also, I think across different model trends, we will gain some intuitive understanding. Maybe not at the classic level of circuits, but more on a level that's a bit more abstract, like architecture and optimization. And the belief for how to get there is maybe simplest in this plot, where on the x-axis, it's plotting the number of benchmarks on a log scale. And the idea is that if you use more and more benchmarks to choose the best model, then the performance of that model on yet another held out benchmark will just be better and better, because you have more and more statistical power and more benchmarks to really choose which model is best at the end of the day. You can phrase this another way, which is basically as you add more benchmarks, you reduce variance in what the model score really is like with respect to all data that you could possibly collect. So eventually, if you have, let's say, 1,000 benchmarks, you would hope that the best model identified by those benchmarks will also perform really well on another held out benchmark that the model has never seen before. And so from those humble beginnings, you might, if you have seen the website, you might have seen that we tried to improve things quite a lot. So new logo, maybe a bit better than the one that I had, and new leaderboard. I think it's a lot more accessible. I know there are still many things that need to be worked on, but this is just to say that we are aware of many of them. I know many of you are logging issues. We're trying to improve things. And now there's also vision and language. One thing I just want to say is with this competition, I think we basically doubled the number of benchmarks. Really, for the modelers in the room, you have a lot more access to a lot of data now that, as I'll show in a second, really hurts current models. There's lots of models. I think there's a lot of community. Maybe one issue that we have right now is that our community is a bit male skewed. If you have ideas for how to make that better, then let's talk about it. And at the time, I think before this year, we had a really good sort of upward trend of more and more models being submitted. There was a peak that you can see in 2022 in the modeling competition, but modelers are, I think, very much bought into this game. Access to data, sure, like it's an easy sell. What I think is maybe has not worked so well is buy-in from experimentalists, which is what prompted this whole competition. And yeah, I mean, I'm not going to read all of this, but a lot of pushback, I think, came from the best models maybe not actually being the best models because they're not being tested on what someone really cares about personally, or that the metrics that are being used are not perfect. And so the idea really for this competition was, okay, if you think things are broken, which probably you all agree on, then we're going to give you money if you improve things. So whole competition pool, and then what I think enabled it was we had a lot of models available, the platform is available, and a lot of data that is just untapped with people that actually know how to work it. And you'll hear from a lot of the people that were able to tap into this data in a second. And so then for the competition this year, we focused on the visual ventral stream, so the areas that Matthias also mentioned earlier that underlie our ability to do object recognition. And we tested basically the models from the 2022 competition that were doing well. We tested the best 10 models as of a few months ago, and then we just tested a bunch of reference models that we thought everyone was interested in. We are in the process of running all the other now 1,500 models as well, so that you can see the trends, but as you can imagine, that takes some time, so it's just not ready for the competition. Before getting into the results, I want to first thank Co for co-organizing all of this with me. I want to thank the MIT Quests, the engineering team, and Eric and Jim also for sponsoring the prize money. So the winners in particular should be thankful, and also the broader community for, I think enabling all of this in the first place. And so now the people that have won the competition, I'm not going to say much, I'll just quickly mention them so that you see who they are. We have 2 winners for each track. So for the behavior track, the winner is Nick Baker, followed by Marin Dujmovic, sorry for mispronouncing. And for the null track, winner is David Kogan, followed by Andrea Costantino. The stimuli are some samples of what they had submitted. You will hear from them if the stimuli are the key idea or what else. But I also want to mention some honorable submissions that I think are worth looking into. So one is by Ben Lundquist, who I think has a really cool benchmark where basically every model scores 0. But unfortunately, he's not eligible for prize money because he's in my group. Sorry, Ben. Then there's Mike Ferguson, who a lot of the submitters should know because he has been tremendously helpful, I think, in just getting everyone's things submitted. And then I also want to point out Linus Sommer from Martin Hubert's group. He, I think, is the only undergrad that submitted, but he actually got things done really quickly, and I think has a really nice benchmark that is worth looking into as well. Okay, some quick stats on what happened. So, or maybe sort of 3 messages. One is, let's, as a community, maybe stop using AlexNet. I think we have many better models by now. For instance, if we just look at the competition benchmarks, so the different columns here are basically all the benchmarks that people have submitted. And then these are the scores of AlexNet, which are pretty red. So you might conclude, okay, so models just don't do this well right now. Well, if you look at a model that is a lot better, like ResNext with massively unlabeled data pre-training, then that does a lot better. So a lot more green, still far from perfect. Like green here just means that it's a lot better, but still not doing everything perfectly. It just means that out of all these benchmark scores, this model tends to do a lot better than AlexNet. And I think there's many other models. So AlexNet itself, in 2024, I think, just doesn't cut it anymore on a lot of these benchmarks. We have better ones. The second message that I came out, I think is pretty interesting, is that if you look at model scale, so how many parameters in the model and how much data is it trained on. So on the left is parameter count on a log scale, with the average score on the benchmarks on the Y scale. Then models that are really small just don't seem to do as well compared to models that are quite a bit bigger. This doesn't mean that scale is the only answer. I don't think that's true, but I think this also says that keeping it super small with current approaches doesn't seem to be sufficient. And the first thing that I think, in the interest of time, I'm not going to go into much detail, but across the benchmark scores, you do see that there's quite some interesting correlations. So some behavior benchmarks that are similar, but then, for instance here, but then also some differences where it's not clear why models are performing really well on one benchmark but not the other. You can also connect all of this to previous benchmarks, but I'm going to skip that in the interest of time. I want to thank Ben here because he made all of these stats and all the statistics. He is also on the job market for a postdoc. If you're interested in a really cool student in the cognitive computational neuroscience space, I think Ben is a terrific person to talk to. And so maybe finally the most important message is that with this competition, there's a lot of new benchmarks now that models just fail on pretty horribly. So even the best models that we have are just not able to predict this data, which I think for the modeling people in the room, this is a potential goldmine where you can really show some improvements over what is otherwise the state of the art, and there's just a lot of delta that you can capitalize on. So let's build better models from that, and let's hear from the competition winners on what exactly makes the models fail so badly on these benchmarks. Thanks.
Hi everyone. So we'll start with the winners of the behavioral benchmark. So our first speaker will be Nick Baker.
Let me see if this works.
Just try to do the classic. Press play.
Yeah, maybe if I just try.
Yeah. Great.
There we go. Hi, everyone. Well, it's great to be here with you, and thanks so much to the BrainScore team for organizing this cool event. So the benchmark I worked on for CCN this year is all about how humans and neural networks perceive the shape of objects, right, and use that for object recognition. So a little bit of history, all of you probably know already. You know, traditional feed-forward networks are not so good at recognizing objects by their shape. So you go from, you know, maybe 90+% accuracy to in the low 40s when you show a silhouette versus a photograph. But this story has gotten better recently with more modern networks, whether that's because of bigger training data or new architectures, I'm not sure why. But these modern transformer neural networks can recognize photographs at like 90+% accuracy and silhouettes at 80+% accuracy. So clearly, networks can recognize objects by their shape, right? The question we were interested in was what kind of shape information these networks use, right? So one possibility is that they really care about local shape. This would be stuff like fur or feathers, or we can think of them as texture-like properties of the object shape. The other possibility is they might care about what I'll call configural shape. This would be like how parts are arranged with respect to each other. And the third possibility is, you know, like humans, they care about both local and global shape, or configural shape. So here's how we tested that. We created these new kinds of silhouettes called Frankensteins. And all a Frankenstein is you take the top half of an object, you flip it around, and you put it on the bottom half of the object. So this is kind of nice because it preserves the local shape information almost totally in the image, but it disrupts the configural shape information. So to the extent a recognition system cares about configural shape, they should be worse at recognizing Frankensteins than intact silhouettes. So we tested that on both humans and neural networks. I'll skip through the details, but they essentially had to do a 9-alternative forced choice task with animals. And here's what we find for humans. Maybe unsurprisingly, humans were better at recognizing intact silhouettes than Frankenstein silhouettes, right? Humans care about configural shape. We have decades of perceptual research that shows that. Not too surprising. Here's where things get more interesting. We tested on a variety of artificial networks, and I understand the BrainScore team tested on several more. Across the board, we found basically no difference in how networks recognize intact whole silhouettes compared to Frankenstein silhouettes, right? So networks don't appear to care about the configural properties of an object shape. And now, maybe the million-dollar question is, why don't they care about this, right? And I'll suggest two possibilities for now. I'm sure there are others. The first is that maybe they just don't need to care about configural shape. They're getting 98% accuracy or something already. Why learn something new and complicated when you're already getting close to 100%? If that's true, what we really need to do is create training curricula that require the apprehension of configural shape, right? Where local contour texture or even texture information are not going to cut it to accurately classify images. And if networks then succeed with this new training program, problem solved. The other possibility, and this is maybe a little more speculative, is that configural shape requires what I'm going to call abstract visual relations. And artificial neural networks, at least the ones we currently have, may be unable to apprehend these abstract visual relations. So if you think of this kind of symbolically as having relations like above, which can take arbitrary inputs, or twice the length of the principal axis, which can take arbitrary inputs, artificial neural networks may not be set up to learn these kinds of abstract relations, and we may need new, more symbolic kinds of network architectures to start to build capacities to recognize objects by their global shape. I wish I had more time to elaborate on that. I've cited a few papers here that talk about this more. But why don't I end here today by thanking James Elder, my collaborator on this work, and the BrainScore team for having me.
We have time for a couple of minutes for questions. So if anyone has a question, please go ahead.
So configuration also matters for internal features, in particular for face recognition. And have you thought about that? And that tends to happen most when you're an expert at some category. So dog show judges on dogs, birders on birds, et cetera.
Yeah, that's a great question. So I have thought about that a little bit. So yeah, faces, I think, are a great example of this kind of abstract process that I think needs to happen. I think especially of when you see a face from a pair of screws and a line or something like that, where the inputs, the pair of screws don't look like eyes, the line doesn't look like a mouth, but when they're configured the right way, they look like a face to us. So a neural network, we haven't tested this, but I wouldn't imagine would ever call that a face, but it looks like a face to us. And I think that is because we're really sensitive to these configural aspects. And like you said, we're so kind of used to and recognizing faces is so important to us, we really are good at picking out these abstract properties of the face.
Those are really interesting results, so thank you for sharing them. One question I have is, you had a slide showing the performance of various networks on the benchmark. Yeah, that one, the one we just...
This one.
Yeah, so what do you make of the fact that the VIT was, already doing this task at higher than a human level? Is that to say, theories about what you need in the model to achieve good performance are like unnecessary at this point because the red is doing really well? Or like, if you think that the gap between red and blue is what's important, then like, obviously, why would you need to have a gap, right? That's not like a thing you would think things would be selected on, right? You think this would be selected on doing well, right? So if we're already doing as well as the human by some of the models, what else do we need?
That's a great question. So I think you could argue what doing well really means here. Like for this elephant, I guess you can't, yeah, you can see my mouse, is calling that an elephant, or is being confident that's an elephant doing well? Well, in some sense it is, right? Because there's, local features that are in common with an elephant. It's more like an elephant than whatever else is in the database. So the fact that a network can do well, do we really want to call that a failure? I would say it's just a difference between humans and networks, not necessarily a failure of neural networks, but a difference between what humans do and what networks do. Because humans look at this elephant on the right and, at least some of the time, more often than the elephant on the left, say, what the heck is that? Networks look at it and they say, okay, that's a great elephant. I would say, if you want to build a network that is going to, have really high classification accuracy, I think we're on the right track. If you want to build one that is like humans, maybe there's still some work to do.
But thank you.
Sure, thanks.
I was just reminded to mention that the winning award was 3,000 USD. So congrats, Nick, again. And now, now I'm going to call up Marin Duzmovic. Jeff, are you going to? Okay. So Jeff Powers is going to give the talk for her. And this is the runners-up prize for the behavioral benchmark award. Competition is also 2,000 USD.
Great. Yeah, I'd like to thank the organizers as well. It's a really, I think, a great initiative here. We're going to talk about some data based on some dotted line drawings and textured silhouettes. So starting off very much less like the last talk, a critical feature of human vision is that it relies on largely shape. So in a classic early study in psychology by Irv Biederman showed that people could identify colored photographs and line drawings at essentially the same speed, same accuracy. There was no benefit. So all the texture, all the color was irrelevant to classifying isolated objects. So that's a critical feature of human vision. Another, a classic finding, well known from psychology for 100 years or more, is that when we see scenes, we organize elements of those scenes by various perceptual organizational principles, sometimes called Gestalt principles. And so we organize these things in ways, and those organizations are critical. There's a stepping stone towards recognizing objects. We organize elements into scenes, into surfaces, into object parts, and those are the representations that are used in turn to classify objects. So, again, so these are, we care about shape and we compose shape often using these various basic Gestalt principles. So that's human vision. Whereas we know that most current models that do well on brain score, for instance, for one thing, they don't care that much about shape. And at least that was true of some of the early models, the classic paper by Robert Garros and colleagues, where they you've all seen this before, no doubt. You put the texture of an elephant on the shape of a cat, and the model confidently claims that's an elephant. They care more about texture than shape, whereas humans would confidently identify that blended object as a cat, not not an elephant. And Chris mentioned a paper of ours by Gaurav Malhotra, where we kind of showed even when we train a model to have a shape bias on one set of stimuli, when train a new set of stimuli, it would go ahead and care more about texture. So there's a very strong inductive bias of these models to care about non-shaped features when learning to categorize new items. So, and also, so humans care about shape, models don't care so much about shape often. And furthermore, humans are very sensitive to perceptual organizational principles, and we've shown some of our own studies that these models don't reliably and capture most Gestalt organizational principles. So the logic of our study was, well, let's make images that are defined by shape that are in turn the product of Gestalt principles. So that presumably would cause these models a great deal of grief. And so that's what we did, and we used, so we've built our kind of something we call a mindset vision toolbox. We have this data set that's now available that you can download, where we've collected about stimuli from about 30 classic psychology experiments, or they're not all classic psychology experiments, but most of them are classic psychology experiments. Others are relevant visual stimuli to test hypotheses about human vision, and it goes from high-level vision to low-level vision and in between. And it was designed to make it easy for people to test their experiments on psychological experiments. And we just grabbed two of these stimuli sets amongst the 30 are the ones we used to generate stimuli that had these properties. So we have, and we wanted to generate things. I mean, again, we care about shape, we care about Gestalt principles, so it should be trivial. And so we picked images that we thought humans would find trivial. So we have, for instance, a dotted set of outlines of objects. So, you have to kind of, good continuation is a classic Gestalt principle. So you can perceive that as a line and you can see that as a bicycle easily enough. Or we have texture where we kind of compose, more like a silhouette, but not a constant silhouette, just a textured set of characters. Again, organizing based on kind of principle of similarity, defining a shape, and humans can identify these things quite easily. So these are all trivially to identify. These are birds. The difference between the left and the right so of these two is simply the spacing between the dots. And here we had just different textured elements. So we had 4 data sets that we composed in this way. Elephants. So, simple experiment, 4 groups of participants saw 10 object categories, 10 members per category, so 100 images per benchmark and 50 participants. And we flashed these images. Oh, I didn't even say, but yeah, so I did. So fixation, flash them for 200 milliseconds, and then you respond, 1 of 5 categories. And not surprisingly, humans find this trivial. So, people were about 95% in identifying these objects when they're flashed. If I understood, I think the one we came second place was based on this dotted outline in this double space condition, which humans found slightly harder, but still getting about 95%, 94% or something like that. Whereas if you look at the performance across all the models, my understanding is the average performance was a scaled score of 16%. I'm not quite sure what that is in raw numbers, but anyways, models did very poorly on these stimuli. So, and a more general point I want to make is that we know good behavioral and brain predictions can be mediated by visual confounds and stimuli. We know, for instance, from from studies that there are shortcuts. And when you kind of identify an image and classify it, it can be carried out by shortcuts. For instance, the Garrow study showed that there was a shortcut. There was texture that was driving object recognition. But those same kinds of shortcuts or confounds, in principle, can be used to classify and make predictions both through RSA or linear regression methods. And so we have 2 of our papers here. One of them, Gaurav Malhotra on Thursday, has got a poster where we kind of show a confound in brain score in fact, it's the background, not the target object that's driving most of brain predictivity in IT. So there's lots of confounds and stimuli, and lots of stimuli that are predictive object category, a lot of features that could be used to predict brain score. And So there, as a consequence, good predictions don't inform you what the similarity, the metric, are they actually similar underlying representations or not? Well, you don't know, because they're confounds, and you haven't, if you use a naturalistic data set in which you haven't controlled or manipulated independent variables, you don't know what features are driving the good predictions. And so this is a figure from our BBS paper where we just highlight this point that the higher the prediction doesn't necessarily mean any better correspondence to the human brain. And what you need to do, in most areas of science, what they do is run experiments where you manipulate independent variables designed to test specific hypotheses and to rule out confounds, finding out what are the features that are driving good predictions. Once you know what the features are, then you can say, are those the same features that drive human performance on a task? So that's, the standard methods of science. You run experiments where you manipulate independent variables. But my critique of BrainScore is that's not what's been doing so far. I think this exercise is great because that's what people are, Chris Baker and us, our stimuli were manipulated. They're artificial in some ways, but they're specifically manipulated to test a particular hypothesis. Is it configural processing or not? Is it Gestalt principles or not? When you manipulate images, you test specific hypotheses, and you can make some kind of informed decision about whether these models are working like humans. And I think the answer is that so far they're not, so that's the message I would like to say about the brain. I guess in the panel discussion we'll have some conversations about this. But I think there's been a mistake in the field of using these observational data sets of naturalistic stimuli, not running experiments to test hypotheses about what is driving the predictions. So that's the conclusion.
Maybe we can take one question.
Thanks.
Great talk. I want to take your suggestion of avoiding confounds one step further with your own stimuli. It has been shown also that these networks often look more at the higher spatial frequencies. So if your images would be low-pass filtered, I think you wouldn't even need Gestalt principles to solve them. So could it all be due to the fact that the networks here, at least for those stimuli that we've used here in the benchmarks, are looking for the high spatial frequencies? So it's a different confound maybe than the one that you think you're...
So are you suggesting that if I did filter the images, that the performance of the model would be better? I mean, if that's...
No.
That wouldn't do it either. Okay.
No, I don't think you would need to test it with images where the spatial frequency spectrum doesn't matter for finding the solution, I think.
Yeah, I think that's right. And that's a concrete hypothesis.
Yeah, it's an hypothesis. Yeah, I totally agree with you. Yeah.
Yep. Yeah, thank you.
All right, sorry. Oh, okay. So yeah, I was surprised that the accuracy for the models that you've tested are so low. I was wondering if it's because there's lack of instruction in terms of what the model should be looking at. Because I just uploaded one of your images to ChatGPT and say, describe this image in one word, right? It'll tell me it's dots. But I have to ask, what object does it represent in one word? And it'll tell me it's a plane, right? So do you think it's the low accuracy of, I think it's only 0.16 is because there's a lack of instruction in terms of what the model should be looking at?
Well, in this case, these models have only one task, is to classify. So it's not really,
Yeah,
I mean, if there were multiple things these models were capable of doing, you need some instruction. But I guess my first gut reaction is that there is only one thing to do. But yeah, did ChatGPT or did GPT-4 whatever succeed or not succeed when you did it?
So
we found it failed on our stimuli when we did it, but
yeah. So basically, when you ask a person, okay, what this image actually represent, right?
Yeah.
And then they tend to recognize it as an object. Whereas when model process the visual stimuli, they could just say, oh, I recognize a lot of dots, so I'll tell you it's a dot. It doesn't really say, oh, it's shaped in an object in the form of a plane. So I think the accuracy could be low because there's lack of instructions into that.
let's stop there.
Cool, thanks. So before going to the neural vendors, I want to make 2 quick points. One is Jim just reminded me that I completely forgot one tiny detail, which is how we actually chose the winners. So basically the criterion was if the average score of all models on your benchmark is the lowest, then you win. So the more you disrupt the model performances, the better. And so now we'll hear from David Coggin on how we can disrupt the neural benchmarks. I also want to point out real quick, at the end of this, we have 2 boxes with T-shirts. We got some swag. So if you want to get some cool new merch, also stickers, please grab those. Yeah, David.
Cool, thank you. So before I get started, I'd just like to acknowledge the BrainScore team, not just for the awesome platform you guys have built, but also for your endless patience with me during the submission process, so thanks. Our neural benchmark utilized an fMRI dataset from a study of occluded object perception in humans. So specifically, we were investigating amodal completion, which is where, despite a partial or fragmented view of an object on your retina, we often still perceive or understand that the object is a complete whole. And in this experiment, we characterized the neural representation of occluded objects across both early and high-level visual cortex, and we tried to understand to what extent the neural representation is completed in the different visual regions. So to do this, we presented these 8 object images without occlusion and then with these 2 sets of occluders, which are complementary in the sense that they obscure entirely non-overlapping halves of the image. And the rationale for this is that it creates 2 different views of an object which complete to the same object, but at the pixel level they are entirely uncorrelated. Well, technically they're anti-correlated, but there's no shared information there. And so therefore, the extent to which you see similar patterns of response, say in a region of the brain or a layer of a computer vision model, is going to give you an indication as to how robust the model is to occlusion, how much completion might be happening in the representation. So we presented these images to 9 subjects while we recorded fMRI at 7T. They were instructed to fixate at the center of the image and perform a basic 2 AFC discrimination task, animate, inanimate. And then we've just performed a basic representational similarity analysis within each region of visual cortex. So we just correlate the patterns of response to the different images to generate these representational similarity matrices. So the primary measure in this experiment was this sort of completion idea. So it's indicated by invariance of the response to the position of the occluders. So on that plot, that's basically the height of the green bar. And what we anticipated going into this, or hypothesized, was that we would see high sensitivity to occluded position in early visual cortex, and then get this like lovely emergence of the completed representation as you move through. But as you can see, that's kind of not what happened. We actually got some pretty strong index of completion very early on from the earliest cortical regions. And this surprised us somewhat, because it seems to be that it's no less strong in V1 as it is all the way in high-level visual cortex in IT. And so after we saw this, I was like, maybe this would do well on the BrainScore benchmark that's coming up, because this suggests that V1 is storing a fairly completed representation, and usually there's a lot of models on there that are sort of they're either feed-forward or they lack the kind of recurrent processing, which we believe explains a lot of this effect here. Just as an aside, we also see a similar sort of uniformity across visual regions if we were going to compare unoccluded and occluded objects. So the difference between the dark blue and the light blue bars is basically the impact on the representation that you have when you add an occluder to a previously unoccluded image. And again, this effect is a little bit stronger, but it seems to be just as strong in V1 as it is in IT. Okay, so to convert that data set to a benchmark, we had to overcome this issue with the lack of measurement noise. So what happens if you put the 24 images into a model, say this is Cornet, and then you get the representations out and do the same RSM, you get this really strong diagonal, because you get this, it's perfect correlation there. And this presents an issue for our analyses because the way they worked is you're kind of comparing on versus off diagonal things, and it sets a really, really high bar for the model, and it seemed a little bit unfair. So with very little time to go before the deadline, we reverted to a more basic representational geometry comparison between the models and the humans. So that's just a fancy way of saying we took the model RSM, we removed the on-diagonal values, and then we correlate it with each of our 9 subjects. So here are the individual RSMs for V4. And the ceiling that we calculate here is it's the lower bound of standard noise ceiling analysis in RSA. So what we do is we take each individual's RSM, we correlate it with the mean of the remaining group, and then we do that 9 times across our subjects. And so the ceiling here is 0.335. That's how well the humans predicted each other. And I'm told that the 19 tested models scored an average of 0.066 on this, so much worse than the humans predicted each other. And if I could speculate on why that is, I think it's probably a little bit to do with like the visual diet, because you see sort of this selective image uploading to the internet, this photographer bias that you see in ImageNet, and so they're not really as experienced with occlusion as we are, but probably it's more to do with, especially since it was one of the earlier visual regions that the benchmark performed so well at, is the fact that there isn't really built in the capacity for recurrence to sort of fill in an object representation over recurrent cycles. Okay, so with that, I would like to mention that we've made both the stimuli and the RSMs publicly available for this benchmark, so you can take a look at them yourselves. And if you'd like to come chat with me, please come find me. If you can't find me, I've got a poster session on Thursday afternoon. And with that, I'd like to thank everyone at the Tong Lab, awesome place to work, and the funding bodies that support my research, and you guys for listening. Cheers.
Time for one question, I think.
Hey, David. Great talk. And very cool data set. I was surprised, though, by the amount of variability across subjects. Were you, and do you have any thoughts? It seems like, in particular, half showed a lot of that blocky structure that you would expect, but the others did not.
Yeah, that's a great point. I think if I was going to run this again, I would definitely get more data per subject. And yeah, some of them are showing a much better or clearer clustering. Yeah, I think there is just a lot of individual level subject noise. That was quite common. So ultimately, a lot of the analysis we do had to be at kind of the group level for the true shape of the data to come out.
Thanks for the nice talk. How do you distinguish filling in of the image from having a receptive field that's just larger than 1 pixel?
Sure. Yeah, so we've actually done some experimentation on this. So we attempted to see to what extent sort of basic receptive field properties could get you sort of above 0 similarity across those 2 corresponding views. And it turns out you can get some, but it doesn't really get you anywhere near the kinds of like completion levels that we're seeing in V1. So if you look at these circles on the left, these are estimated PRF size averages in V1 in a human subject sample. We then created we parameterized the pre-existing V1net model to have a receptive field size on average, the size of that circle, but the kernel size is much bigger, so it can integrate information more. And the performance is on the right, so the completion is still way lower than we've estimated in like V1 across multiple experiments. And it's mostly sort of driven by that negative correlation, which we use to baseline this estimate as well. So yeah, it gives you a little bit, but it doesn't give you anything like what we're actually seeing in human visual cortex. Thanks.
Thank you.
Cheers.
Okay, next up is Andrea Costantino, who won the second prize in the null track. Same prize money as in the behavioral one, so this is 2K to you. Please, Andrea.
Thanks. One sec. Yeah, I don't see my mouse. Second. Yeah. You know where?
Are you a big PowerPoint person? Yeah, slideshow settings.
Brad, I'll try to connect again then. Because probably we need to do it on the other screen.
And then, okay, yeah, let me have a mouse. And then,
Yeah.
Yep.
All right.
Yeah.
Okay. All right. So first of all, I would like to thank Martin and the BrainScore team for organizing the event, the competition, and giving me the opportunity to be here and talk about our submission. And then I would like to stress that this is a shared submission, and so I would also like to thank my collaborators, Hans of the Beck and Stefania Bracci. Okay, so I want to start this talk with a brief behavioral experiment. So I will show you 3 images. So the image of an object, the image of an animal, and a third stimulus. And I'm going to ask you if this is more similar to an object or an animal. Okay, most of the people here would say that this third stimulus is more similar to an object, as you would have guessed, because it is an object. And we can plot this kind of behavioral responses. We can plot it on a 2-dimensional representational space, and we can do it for another triplet and another triplet and so on. And eventually what we are going to see is a clustering like this one, where, let's say, lookalikes are more similar to objects than to animals. This is what we call an object bias. So this is a tendency to judge lookalikes as more similar to objects than animals. And this is what is at the core of our submission. So this is a data set that was developed by Stefania Bracci in 2019. So here you can see basically 3 different categories of stimuli where you have animal, objects, and lookalikes. And basically in this study, the subjects were presented with this data set while they were lying in a scanner, and they were asked to do a similarity judgment task. Okay, so in terms of results, as we mentioned before, results from the study essentially show a weak object bias at the behavioral level, where lookalikes tend to be judged as more similar to objects than animals. In terms of DNN activations, we also see a strong object bias where lookalikes are basically mixed with objects, but they are still very distinct from animals. Okay, but the most important thing here for the competition is actually the brain activations, which show an animal bias that is very different from what DNN and humans do. Okay, so in this case, basically, the lookalikes are more similar to animals than to objects. I would like to highlight that these results are not spurious results in the sense that they were replicated internally across 2 different tasks. They were replicated with a EEG experiment, and they were replicated with a computational experiment where we tested several very specific hypotheses about let's say, the basis of this animal bias. Okay, so overall, these results tell us that, so first of all, they show us a human brain failure in object representation where the brain is actually wrong in some sense, or at least the areas that we explored, is that they are wrong in some sense, right? Because they categorize lookalikes as more similar to animals than objects. But most importantly for the BrainScore competition, we also see a strong discrepancy between brain and DNNs that was confirmed by our computational experiments, but it was also corroborated now by the BrainScore results. Okay, I would like to end this talk by briefly touching on a few points that I think are important lessons that we learn from these results. So first of all, the well-controlled data set. So first of all, these results, along with the achievement on the BrainScore competition, demonstrate how a carefully controlled data set and design can provide informative insights about what is behind the failure of the models, even within more predictive rather than purely explanatory modeling frameworks. Okay, so this has been touched already in previous talks. So in natural images, we have a lot of features, and these features tend to covary and correlate with each other, so they carry a lot of confounds. So big data sets like ImageNet and so on, they carry a lot of confounds that you can actually control with these smaller data sets. Also, these results, they show how DNN can be a powerful and versatile tool. So basically a computational language to test very specific hypotheses about psychological phenomena. So overall, this achievement illustrates the relevance of the experimental approach on one hand, combined with the strengths offered by DNNs as image computable models with rich and high-dimensional representations that we think are needed to understand representational complexity observed in the brain. Okay, so the predictive power of these representations, along with the explanatory power of controlled experiments, can move forward our understanding of biological and artificial vision systems. However, these results also suggest that maximizing alignment with the human brain may be not what we want, may be not sufficient to build better model of visions, and can even result in conflicting demands, right? So for example, here, if we want to optimize to, let's say, predict the activations in IT, we can have models that actually underperform, models that actually, that they are wrong behaviorally. And that's it.
Hi, thank you. So my question is, how much do you think the instructions that are being given to the participant and to the DNN is affecting the alignment scores? To echo a previous question, if you added something like a text encoder to go along with the visual encoder, do you think that that way it would then have, you would fix this alignment problem?
So this is a very good question. So we got this kind of questions from reviewers in the computational paper specifically, and you can see we also use CLIP, for example. There is a language-informed model, and we saw the same exact results. So basically, the DNN have an object bias rather than an animal bias. So I mean, these are all hypotheses that can be tested. We tested one of them, but.
And with CLIP, what is the text input that you're putting in?
Say again?
With CLIP, are you just using the visual encoder, or are you using any of the text encoder as well?
We are using the visual encoder.
Okay, if there are no more questions, then let's thank Andrea again. And so now we'll have giving, I think, a high-level overview of what maybe doesn't work well yet, also as a way to set up the panel, which then Jim will moderate. And yeah, please go.
Hi, everyone. Thanks for coming and attending this session. So I just want to say that, like, it's very nice that many of you had thanked me as a part of the BrainScore team. I'm like a distant cousin of the BrainScore team. So I'm not like literally part of the BrainScore team. I have been kind of like a, appreciator of BrainScore, but a reluctant contributor to BrainScore for a while. But I think I'm, changing my views. So I'll set up some thoughts, and this is going to be more like of like a broader overview of like how I think about it and how I've been influenced to think about it. So it's about the BrainScore, benchmarking competition. And I was trying to come up with a title that could fit my talk, but I think this is the closest I could come, like nuances in building benchmarks, but it might not be, the talk might not be fully aligned with this title. So let's start. So I like to think in metaphors, and I'm going to use a metaphor. So this is me, and I'm trying to touch the bottom surface of the moon or some part of the moon. And I think this is how I also think about like making progress in neuroscience, right? And I'll say visual neuroscience. So I think that one of the things is that I can raise my hand and I'm not touching the moon. That much I can say. So, or I can measure the distance from the moon, and I have a ladder to sort of like go to the moon. So if I measure the distance and I say, okay, the top of the ladder is like some distance away from the moon, if this distance is very small, then I can my strategy is to add more rungs to the ladder, right? I'm not going to do something drastically different. I'm almost there. So I'm going to go, and then I'm going to reach the moon, right? So for the rest of the talk, I like to think of the moon as some sort of like idea of data in neuroscience, like what we mean by the brain and like how can we probe the brain. These ladders are the models. And the model improvements are these rungs, or however which way we are going to change the ladder or whatever. But there's also an interesting thing about like how do I actually measure the distance? So there could be many ways of measuring distance. So I'm not going to talk about that. There's also actually another event called the Battle of the Metrics that you might be interested that might actually more explicitly talk about the thing. So that's one situation. But imagine I'm in a situation like that where I'm there and the moon's over there, and I can still measure the distance. I'm not probably going to, build a ladder to get to the moon in this case. So my model improvements actually depend on like where I am with respect to the moon. Right? So I think we should appreciate the fact that if we have the data and we have the model, we at least know how far we have to travel. And that's all about benchmarking. And this is actually the most important thing I feel like BrainScore is contributing to the field, beyond some other obviously important things as well. Okay, so this is the current BrainScore platform that Martin showed. I'm going to start showing a few things that provokes me to think about it in some way. So I would say that, okay, sorry, one point I wanted to make is that if you take the best model here, like 0.53, almost halfway there for overall brain score, and maybe like the best scores are 0.6. So you can think of this situation like this, okay? This is like somewhat influenced by what data was available, what we could put in. So the latter is almost halfway there or not halfway there, or a little bit higher than halfway, right? Okay, so one group of us who has access to the ladders, like we can play with models, we can collect data, or we do talk to experimentalists. We can measure ourselves, and we can say, okay, here is my situation, that I'm halfway away from the moon for core object recognition, right? So I got to improve this a little bit. So if you think of the problem like this, it feels like we got a big enough ladder. All we need to do is get some data, add these like bits and pieces, and we'll get there, okay? So that's the obvious strategy if you think of the problem like this. But there could be another way of thinking about this, that we have a ladder, but we are looking at the moon through a telescope. And we are saying that, hey, the ladder has reached the moon. But we are completely doing this in denial of like where the moon actually is and how faulty our measurements are, or how faulty our metrics are, or our models are. So I think a lot of people would look at the current scores and be like, you know what, I don't think this is the right demonstration. Like, this is the right demonstration of the world. The right demonstration is like that. But and I don't know, personally, I actually don't subscribe to the top view. But I'll tell you a few reasons why that kind of things might come up, why that kind of feelings might come up. So the first one, okay, and what that literally means is that whoever is claiming that the moon is not there, the moon's actually over there. So if the moon is over there, we have a big distance to cover, okay? So if you look at a platform like this, and if you look at the neural data, so there's like some choices been made, right? V1, V2, V4 IT. Why not, some other area? Why not the dorsal stream? There are enough papers to say the dorsal areas are also relevant to object recognition. So some people might be offended, like, why is my favorite area not here? So I don't care about this ranking anymore. There's behavioral stuff, which is like, why is my behavior not here? And I actually totally agree that this is actually a justifiable, frustration, because but what I will also like to channel is that this whole process of benchmarking is as much a social process than it's an objective scientific process. So I think these kind of events, we need to come together. I'll try to motivate a little bit later. So who chose these? And why those? Like, why V1, V2, V4 IT? So there are reasons for these, these choices initially. So can we agree on shared goals driving these benchmark choices? Like, do we have shared goals in the fields that can actually drive those choices? And I think my answer is like, there probably isn't. There should be, but there isn't. And do we need to agree? Like, some people might say, oh, why should we agree and, zoom into a local minima? Maybe we don't need to agree. So that's one side of the problem. The real problem, or like, to me, what feels a little bit more real is that if I look at BrainScore and I look at the top model, if I look at V1, V2, V4 IT, they're all part of the same layer of the model, right? So automatically, I get a feeling like there's something like wrong. Like, I don't know what it is, but something wrong. Then you go to the second model. Sorry, the first model, the first three are the same. The second one is, the IT is different. The second model, all are the same blocks. They're all the same blocks. So V1, V2, V4 IT is the same part of the model. The third one, V1, is actually later than V2 and V4. Okay, so as a physiologist, I'm sort of frustrated, I'm offended, I don't know what it is, but what it really means is that I value certain benchmarks more than some others. Like, I think this idea of like the physiological latency of the responses that sets up this hierarchy, I value those benchmarks more. So there is that, but who am I? Like, who decides this? How do we decide it, right? So I think there should be some considerations of like, how do we go about answering these questions? And to me, this does not throw BrainScore out of this scenario. This is the same thing I was thinking when Jeff mentioned this thing about like this specific hypothesis testable ideas, and I think these sort of like way of testing model is exactly what we should be doing, and we should be doing within a parameter like this where it enables you to test those models. Like when ImageNet came up, adversarial images were not known at the point, maybe known to somebody, but it came up later. We didn't say ImageNet wasn't useful. We still have benchmarking computation. So I think those two are separate problems in my head, but I think these kind of events actually allow us to talk to each other and figure out like how do we combine these frustrations and do something more productive. So the suggestion I have is that initially we just had that, one arrow from maybe one lab or two labs. Now we need to engage and diversify from these folks who are actually thinking about the same problems in their labs. So we should engage and diversify this, the benchmarks and how we think about this. The other question is, can the new data tell us how to improve? Like we get some new data, we get this, like we have this competition, we have these new benchmarks. What did we learn about the strategies to make better models? And can we improve in the same way? Is that just more data? Or what are the strategies? Of course, we heard some strategies today from folks who I would claim as they belong in this part where they're actually like dealing with all these components. There's also another set of people who I think, arguably for me, has been most influential in this whole game. It's those people who have a different moon. These are folks from AI who have nothing to do with the brain, but they're just generating models to reach their own moon. And I think we need to pull those models into this benchmarking system. So as I'm saying this, and I was actually making the slides, I realized what PhD student is going to take up this project, who's going to fund this project. It means talking to like cognitive neuroscientists, system neuroscientists, AI specialists. You need to have software engineers managing that platform. This is not an easy thing to do. Like you can tell whatever you want, try and implement one of this, you will realize where we are and why we had to start with some of these specific benchmarks, right? And on top of that, another interesting thing is that there are other folks who just like to look at the moon in different ways, So these folks are experimental people who don't necessarily, engage with image computable models or any model sometimes. But honestly, when I look at their papers, I think they're collecting the most interesting kinds of data. So there has to be also a requirement to somehow interface with them and get their data into the platform as benchmarks, right? So again, these are the complexities that are really at play here, at display here. And I think these kind of discussions that we'll probably follow are the right sort of moves to go forward, sort of, harmoniously together. So that was my talk. I quickly wanted to thank Jim and the team for actually developing BrainScore and having all these stimulating conversations in the lab. And for Martin for tagging me along and for your great friendship throughout this time. So and I have my new labs and I also try to discuss this stuff with my folks in the lab. And thanks to the funding agencies for letting me come here and playing for the flight. Thank you. So next up is, I think we should have the panel members come up and bring their own BYOC.
Okay. Hi, everyone. My name is Jim DiCarlo. I run a lab here at MIT, and I've been a big supporter of this effort that Martin's led in BrainScore. I want to start by thanking Martin and the team for organizing this, Martin and Co., I guess. So thank you. Round of applause for you guys. So I played hardly any role in this competition other than to cheerlead, but now I was asked to just moderate this panel discussion. So I gave these guys all a bit of questions ahead of time, but I'm first going to ask them to just give their 10-second introduction to who they are and any relationship at all to BrainScore. So let's just go around, and why don't we start there? Go ahead, Dan.
Yes, I'm Dan Yeamans, and I'm in psychology and computer science at Stanford. was here in Jim's group prior to the launch of BrainScore. So, you know, I've been seeing it for many years. I should say I'm on the board of the BrainScore advisory board. Okay.
Hi, I'm Eva Fedorenko, and I have a language lab here at MIT. And I guess a version of language BrainScore is the plane we were building as Martin and Greta and others were writing the first paper and relating a whole bunch of models to a few benchmarks we had in the lab. So that's been my involvement.
Hi, I'm Janelle Feather. I'm currently a postdoc at Flatiron Institute in New York City, but I will be starting as an assistant professor at Carnegie Mellon next year in 2025. And so my relationship to BrainScore is that I did my PhD at MIT sort of while BrainScore was very actively being developed. I was thinking a little bit more about benchmarking things on the auditory side, which I think would be really fun to expand BrainScore at some point into. But yeah, I'm excited to be here.
Yeah, I just gave a talk. I'm Koidish Karko. I was a postdoc with Jim, and now I'm an assistant professor at York University. And I'm also in the BrainScore advisory team. But yeah, I saw BrainScore develop from scratch via Martin and Jim and others' effort. So I'm hoping to contribute more to BrainScore. I have contributed a little bit here and there on the benchmarking side. So.
Yeah, and I'm Jeff Bowers, professor at the University of Bristol in the UK. So I'm not linked to BrainScore. I guess I'm a critic of BrainScore, so that's maybe my role here.
Okay, good. We'll try to tap that, Jeff. So let me just try with the first question. Real quick, I want one quick answer from each of you. Does the field actually need platforms like BrainScore? You can say yes, no, or maybe, and then we'll expand, okay? So go ahead, Dan.
Oh, yeah, definitely, because without it, you'll never
Wait,
know.
that's more than one word. Yes, no,
yes.
or maybe. Yes,
Sorry.
okay.
Yes.
Wait, I didn't hear from Ev.
Yes.
Yes.
Jeff?
I'll say no.
Okay, good. So there's 4 yeses, and we can maybe have them elaborate, but maybe we could start with Jeff. So the field does not need a platform like BrainScore. Could you tell the audience more of why you think not?
Well, I guess it's just the approach that I think so far. I mean, I think this what we're doing right now is great, which is maybe transforming what I've seen with BrainScore. But again, like I briefly said before, I see BrainScore as an approach of science where you're using big observational studies without manipulating images, testing hypotheses, focusing on the basis of the predictions, just looking for higher scores, which I think makes a lot of sense in an engineering context, but in a scientific context, I think it's leading to blind alleys where you kind of working harder and harder to get a high score and often just, but in the wrong space altogether.
Okay, so Jeff's worried a bit about just chasing the benchmarks without gaining intuition of the models along the way. Just channel some of what you're saying.
Yeah, and with a particular focus on, I mean, the people people are manipulating models, but they're not manipulating images. It's focus on naturalistic image data sets, I think, is leading to mistakes.
Okay, so good. Does anybody of the yesers want to comment on that or disagree or agree in any way? Anybody want to chime in?
Yeah, I'm happy to disagree, because if you think you have an idea or a hypothesis, you can encode that as a metric. And you can choose whatever stimuli you want, whether it's natural stimuli or non-natural stimuli. Once you've done that, to judge correctness, you have a notion in your mind of what correctness means. And it has to be able to be quantified, or else you can't say it's science. So if you've got a definition of what's correct and you can control the stimuli, then don't you want people to, quote, chase the benchmark of satisfying a model that will do on the stimuli that you think are important, being good at the metric that you think success is?
Yeah, of course. What I'm saying this session where people are running experiments, so they're testing hypotheses, is a good approach. I mean, the word benchmark is being transformed into an experiment. I mean, if you run an experiment where you manipulate with a particular hypothesis in mind, of course, I'm a psychologist, I run experiments, but my objection has been, for a while now, there's been this pursuit of predicting and making strong conclusions about the similarities based on working with naturalistic images and not knowing what the basis of the predictions are. So, but yes, if people change their approach to do experiments, then I'm totally on board, and that's what we've been doing, and that's what I think everybody should be doing. So it's not against experiments. It's observational data sets without controlling the materials, testing hypotheses.
Let's let somebody else weigh in the middle there. Any of you three want to? Sure.
Yeah, I'm actually really sympathetic to the over-obsession in the field currently with naturalism. I think that has taken back a lot of progress that has been made in thinking about a lot of problems, and people kind of think it will just, once we know how to predict brain responses to some naturalistic stimulus, we'll understand everything, and that's just not going to happen. I mean, I work in the domain of language, and just too many things are confounded, and most linguistically interesting things just don't happen in naturalistic work because it's all like high-frequency words and easy constructions. For language, we started with data we just had available because there is also a host of complexities in collecting high-fidelity, item-specific responses to language, because unlike vision, you can't just present the same image 100 times and get a really reliable response. It's really annoying in that way. But so we just had some stimuli that we had collected data on for whatever reason. We started with those, and so that was the initial thing. But since then, Greta Tuchkuta, Iqbal Hosseini, a lot of others have been collecting data on exactly the kinds of things that you were pointing out, Jeff, like including controlling for particular things, or even selecting sets of stimuli that specifically are designed to discriminate best among some class of models, or to then get insights into why and so on. But I do hear you on naturalism. I think the field has gone way, way to the dark side with that.
Janelle, yeah.
Yeah, I mean to chime in, I also just agree about thinking about more targeted, maybe synthetic, experimental stimuli. And I mean, this debate has went on since sort of whenever people first started collecting very naturalistic data sets, right? Like I know that Nicole Rest and Tony Mobshin had this like really nice article in praise of artifice in like the early 2000s, right? And so this like even predates sort of this idea of benchmarking. It's just like whenever you're designing an experiment, what types of stimuli should you actually be using? And so I kind of think about, I'm like really happy now that like some of these, what some people would call like out of distribution or like very targeted types of stimuli are being added to the BrainScore platform, because I think that that is where it needs to go. But I guess I want to pivot a little bit to just say that like I think that that is like kind of a separate issue than like having some sort of publicly available benchmarking system. And I think that BrainScore, in a way, like it really is it really does a lot for the community in terms of reproducibility, because actually running somebody else's data set and metrics in exactly the same way on your own system can oftentimes be very, very, very hard. And the actual platform that has been built where you can submit a model and get it scored on various data sets means that I think that like if we put a little bit of trust in the BrainScore developers, which I hope that we do, that means that we can sort of trust the results in terms of which models are actually doing better on the various benchmarks, which I think is a really good thing for the community to have.
I want to add one more point. I think I partially agree, and there's some points of disagreement. So there is an example in the exist. So I think there is a debate about BrainScore as it exists today and how we vision it for tomorrow. So in the BrainScore that exists today, there has been a couple of occasions where there has been targeted experiments. So for example, we did a study together where we had models compared to humans, and image by image, and we decided like which are these images that are different between humans and models, and then we had developed like a whole bunch of recurrent networks based on it that solved that problem. So that is not like, maybe those are not the exact same experiments that others were doing, but this was also sort of like a little bit of a hypothesis testing with the existing set of models. So some attempts like that has been done, not at the level that it should be done. So that part I agree. But something that I want to point out is that sometimes like when we have a very specific hypothesis, then it ends up being like, it could be that we will overfit on the solution a little bit towards that. And I think BrainScore kind of like, is sort of guardrails against that by then testing the models across all other possible benchmarks, and to show that, you improved on that particular thing, but then you didn't really like improve on the others. So that's also an advantage that I find that even the current BrainScore sort of has as it exists today. So yeah, those would be my 2 points.
I would just like to comment one more time on this. My understanding, having been close to and then a little bit further from brain score is that there's no bias towards natural stimuli in the people who running brain score's mind, right? Like, just to put it in context, I think there's a mantra that a correct model should work on all stimuli, whether or not they're natural or created by you in some way. And that's a very deeply held belief in the brain score context. So to the extent that there's a bias in using natural stimuli rather than like stimuli designed to test a certain hypothesis, I think it's just those were the things that got contributed effectively. So to put that a little more context, right now the metrics for, there's metrics for different neural alignment on different brain areas. And for V1 and for V4 and IT, they tend to be more natural stimulus biased. But for V1 and V2, almost all of them are tested on the standard hypothesis testing, artificial so-called stimuli. And that's because the people who did the neural collection on those areas, those are the stimuli that they cared about. And so the models, to be good, have to do well, got to do well on V4 and IT and V1 and V2. And so, I think it's just the people in the field have different hypotheses and the different things that they're testing. And sometimes the hypotheses are better tested by natural stimuli, and sometimes they're better tested by artificial stimuli. And so I would suspect at this point that the majority, or some decent fraction of the actual metrics currently on brain score do contain artificial stimuli. So I think it's like, maybe there's like a sort of a stereotype of what's on brain score, but I think that stereotype is not true.
Well, the critical point isn't whether it's natural or not. The critical question is whether the stimuli are manipulated in ways to test a particular hypothesis. And focusing on the data from IT and was it V4, those stimuli are not designed to test what is. So we have this poster coming on Thursday where we take a data set from brain score where we have the IT or V4 where we have an object in a random pose on a random background, and we ask the hypothesis, well, what is it? Is it the object or is it the background that's driving the prediction? So that's a hypothesis, and you have to manipulate the images to answer that question. And so I won't speak to the V1 data so much, but the point is, people aren't asking the question, what are the features that are driving good predictions in these models in brain score? Because you wouldn't know until we ran this study. You didn't. This is a model of. It's supposed to be a model of core object recognition, and you don't know whether it's the background or the object that's driving predictions. And so I can tell you on Thursday which it is, but you wouldn't know unless. And you could run brain score, you could run more and more images, you could do it over and over again. You would never know the answer to that question unless you manipulated the images in such a way that you dissociate the object from the background. And when you do that, and that's like what Robert Garros did. He says, you could run brain score all you want. If you ask the question, is it the texture or the shape that matters more? It doesn't matter what brain score you get. You could get 100% brain score, and you would not know unless what you did was what Robert Garros did, which he says, I'm going to manipulate the image and put the texture of the elephant on the shape of the cat. That's an experiment to test a particular hypothesis, and there is no way to get around that unless you manipulate the images to test a particular hypothesis. And that's what brain score does not do.
Could I try to summarize the discussion? Because I think there's actually a bunch of agreement, and maybe Jeff will push back on this, but I think there is agreement, maybe even among Jeff, that the field needs platforms for reproducible tests of things, Garrios and others. Every paper that's been done, ideally, somebody submits a model, as Janelle said, and you can get reliable scores back. And that's, as Co pointed out in his talk, hard work for teams of engineers just to stand that up and keep it going. I see you nodding, Jeff, so in that sense of a benchmarking open platform, you might agree that that's a necessary component. That was always the reason for brain score. There's a secondary inference, which some of you are making, and Jeff's making strongly, that the purpose of brain score is to, in some sense, substitute for the hypothesis, for being the scientist in hypothesis testing. That is not the reason for brain score, was never intended to be. And so you could use brain score to then follow up with various things. And so Co was making this point. Brain score is essentially that delta measuring device, but it rolls into the fact that sometimes people take the chosen benchmarks as traditionally how we as scientists has engaged in hypothesis testing, especially vision scientists. I would turn the crank one knob. So just seeing that, we may have agreement on all of that, but I'll just sort of turn the crank one knob to say, you could always imagine, no matter what the hypothesis is, what is the next move on the model build? And I think we could have a discussion about how do we think that, maybe this is my next question for the panel, as you look at a set of benchmarks and deviations, we saw today a few benchmarks that models failed poorly on. And maybe, as Jeff said, oh, we had intuition, let's design those and we'll show they form palely, and we'll show it's because they're not doing X, Y, or Z in his version of the telling. But we could do that with any of the benchmarks or even any of the images within the benchmarks. How do we as a field react to those deltas, to Coe's delta to the moon? I would posit there's a large divergence of opinions there, and I'd like to hear from this panel as BrainScore as a public measurement tool, not a here's telling you exactly how to build the best model tool, which is a difference, to be clear. How does this group think about who should be responsible for building the best models, and how does BrainScore contribute or maybe not contribute to that goal, which is sort of what I hear Jeff saying. Like, how does it drive the field forward to the next models of the system that we all care about and are trying to model? So that's my next question in a long-winded way. Do folks have comments on that? Maybe no one cares. Well, I have another question if that's not exciting. Maybe I said it too. How do we react to benchmarks as a community to build next models? How should that go as a social process?
Well, I do have a comment on it, but I feel bad that I've been talking so much.
Okay.
So.
Sorry, I feel like I've been talking too much. Go for it, Dan.
Well, okay, I think one part of it is that better understanding of what the things on there are. So you said there's no hypothesis, replying to something else, which I think is a really critical part of this. Well, there's two things. One of them is you said that there was not a hypothesis being tested by benchmarks like, neural predictivity on the Hung, this particular data set, and, only having natural stimuli in it. But that's not true. There was a hypothesis in the minds of the creators. It just wasn't the hypothesis that you would test. What was our hypothesis? It's we wanted to see how well models optimized for something like a categorization goal on the things that the supposed animals, the simulated animal, the model, would see in the world. How well does that drive IT predictivity on other data sets, basically? And that configuration was our hypothesis, that models optimized for things in the real world, like mostly stimuli as you draw them from the distribution of natural images, would drive a lot of responses. Whether the test data set was confounded is a different story. But that confound is only a confound if you have a certain hypothesis in mind, okay? But it's all a certain idea. The confound you mentioned actually isn't a confound for us because we're talking about neural responses to things you might see in the world. Now, that doesn't necessarily mean the neural responses are true for all stimuli, and maybe if you put certain stimuli in that you think are going to distinguish between models, that we should do that. But the hypothesis we were testing at the time was different than that. But it was a hypothesis, okay? So I think not picking stereotyped broad objections and being, well, that system never would imagine they were not interested in hypothesis testing. I think a better route is to ask, what hypothesis were you testing? As if somehow we were different than scientists in some sort of engineering-y way, as opposed to actually trying to test something about the world. But the other thing I think was when I saw that you were going to be here and that you had one of the winning metrics, I thought, oh wow, this is great. So because it's if folks who traditionally haven't thought that what's been doing in BrainScore is actually science can participate in a way that they think is important, and the rest of us will benefit from because now we can test on your benchmark, right? Then that would be a really good outcome, right? I actually didn't submit any metrics to the benchmark because I was like, it's not important if I do, right? If I want people who have a certain experimental hypothesis and have not been engaged to submit benchmarks, to make submissions, right? Hopefully I'll submit things later.
Next time, please.
Yeah.
Please do.
Yeah, yeah. Well, I just felt that what we really wanted to test was that we could see that if people think, okay, BrainScore is stereotypically this or that, can see that independently of whether they believe this stereotypically, they can participate and they can change people's view of what metrics people should test. For example, if we've gone too far in using natural stimuli, then if they can submit something that will be really effective at model separation by virtue of using certain hypothesis testing-based stimuli, that's the thing we really want.
Janelle, it looks like you want to say something.
I wanted to go back to your original, I wanted to go back to the question, but I agree with what Dan was saying as well, which I think your question was basically how do we take BrainScore and use it to develop new models? And I think that currently for me, the most interesting part of BrainScore and the metrics of model comparison that we are making right now is actually the behavior and not the neural data. And so I really liked the behavioral track here because I think that the behavior is really telling us ways that our models are failing that are potentially more interpretable than some of the other measures that we have right now, where we can say, okay, well, I mean, everyone uses sort of the texture shape bias as one example, right? And so it's like, okay, well, this texture shape bias is in a model, so now we have an idea that this is in there, and so let's come up with some way to fix it. But once we come up with that way to fix it, I think that we have to go back and still test that model on, for instance, natural images. And it's really good to actually test it on those neural predictions, because if we see that we fix the model on this one specific type of data, but now it's failing suddenly on everything else, then that seems like we still need to make some improvement. We've like fixed something over here, but have really broken a lot of stuff on the other side.
I actually want to quickly follow up on Janelle. So I think Janelle made this point, which this has caused me a lot of depression thinking about science. So I think Janelle made this point that like the behavioral benchmarks were the most like intuitive ones for experimenters to like act on probably. And I think this is the part that really depresses me because I think there's this notion that there's an experimenter who develops some intuitions or insights and then is part of this loop that changes the whole, like, contributes to the next move. And I think this is the same need that drives, interpretability for models and all that stuff. So while I totally agree that behavioral benchmarks might be the ones where we have a clear idea of what to do next because we had access to behavior, our own behavior, while designing those choices. It might turn out that not too far from now, there will be, using a platform like BrainScore, there will be models suggesting, changes to themselves. And like, I feel like we can literally write down all the moves that we can make in the modeling, parameters right now with the existing knowledge about what we know about the brain. Like, what are the other components in different ways that we can combine? And some people might call that architecture search or XYZ. So as we get better at that, the game might just be, step out and just let this system, figure itself out. And I don't know what will happen to my job or what to the field at that point, but I think that's not too far away.
Okay. Jeff, something quick you want to say, or I'm going to switch topics?
In terms of, the thing about doing hypothesis testing in a directed way is it does help you know what ways in particular you need to fix your model. So when Garros did his study, it was clear that we need to build a shape bias. If you didn't have his data set and you were working with the BrainScore data set, higher and higher numbers, you wouldn't know that there was this problem with not perceiving shape and emphasizing texture. Or you wouldn't know that your model isn't implementing Gestalt principles well enough. So the good thing about running experiments testing particular hypotheses is it does give you a direction about how to improve models. And just very briefly to push back a little bit on Dan's point, the hypothesis isn't just that you can predict. The hypothesis, I think that the conclusions people are drawing is that these models are, the better the prediction, the better the model is in core object recognition. And so it's not just prediction, it's a particular type of prediction. It's a prediction that's giving insights into core object recognition. So what you need to do is do hypothesis testing on things like, well, if this is a model of core human object recognition, does it care about shape? Does it care about Gestalt principles? It's not enough to say, I was just looking for better predictions, because the better predictions might be the background. It might be based on the texture. So you need not, The conclusions ones draw, you need to have the corresponding hypotheses assessed. And I think people are making strong conclusions about core object recognition, having not tested the hypothesis that it's the object, not the background, that's driving prediction.
Okay, so let's, there's a lot to comment on there, but I think in the interest of time, let's move to a more simplified form of this constructive version of, well, if you were each to improve one thing on brain score, what would you, like just one thing, and these are concrete questions for some of the engineers that are in the room, what would it be?
Do we have to do it in one word?
Well, no, one thing, not one word, but one word would be great if you could pull that off.
I would disband the composite overall score, okay? Because I think that, for instance, the model that was shown as being number one, at least in the thing that was shown there, is a model out of my group. Well, actually, my student one, who I think is here, downloaded a model off the web, a particular architecture model, and then it comes up as being the best model. But actually, I don't think any of us really buy that, because the way it comes up being the best model is because it has a very high score on some behavioral consistency and not quite such good scores on neural metrics, but somehow the aggregation process puts that together. So actually, this is related to Ko's showing at the end, which is who judges which metric matters most. And I don't think we should be doing that all. We should be not aggregating, or at least not aggregating if the metrics have, pairwise consistency that is not very good. Maybe you could look at the consistency, the correlation of the metrics to get clusters or something in a natural way. Okay, that's a separate question. But the aggregation, I always find that information, personally what I use the brain score is I put one metric, low-level metric on one axis and one on the other, and that correlation is really more interesting to me than the score, and I always find that the more disaggregated the things I put on the axis, the more interesting results I see. So I would remove this idea that there's a competition to win the overall thing. I mean, eventually, when all the metrics are correlated for a set of models, those should be the best ones. But right now, since that's not the case, I think if we're trying to, quote, beat the benchmark, I don't think we're likely to get good insights. And a related question is basically, when somebody is concerned about, say, for example, the one that Ko brought up is the hierarchical neuroanatomical consistency is wrong for many models. And I find that a really important metric, and it was actually one of the things that was good about some of the early models. They had that property. And I always look at that metric myself, computed myself, and if that's wrong, I'm very skeptical of a model. So, okay, maybe other people don't care about that. I've been trying to lobby for a metric like that for a while, and we haven't seen it. I don't know why, but hopefully, it's just a lot of work to put the metrics together is basically a problem. But we should not be aggregating. Or maybe if we are aggregating right now, it should be in a much more smart way.
Okay.
Right.
Dan says don't aggregate, and he proposed some other metrics that you guys should submit.
Yeah, and also not make the dumb aggregations the focus of the thing, so that basically you end up not getting insight.
Okay. Ev?
This is inspired by a discussion with Greta Duchkuta. We think that having more flexibility in how ceilings are computed, or more care in general about that, especially given the differences between domains for how that may work, would be really helpful. But just to add to that also, I think it would be helpful to try to incentivize data submission in some way. Because as of right now, the most valuable things, models are cheap-ish, well, it depends. But data are really expensive. Data is what takes, painstaking, many hours. All of you who collect data know this for both animals and humans. And then, once we collect a data set, my first priority is to protect the interests of the junior scientists who collected those data. And that may slow down this communal process of trying to aggregate this all in one place. And I don't know quite how to think about that yet.
Or just comment on what a better way than to incentivize submission of data than to have a benchmarking competition with prize money. That's a cool idea, right? So here we are. But there's another point you mentioned about incentives that if we have time, I'd like to maybe return to. But Janelle, what would be your one thing? What would you improve?
Yeah, I think that maybe thinking a little bit about how BrainScore could separate out the data sets from the actual metrics that they're being evaluated on. And what I mean by this is that we have various data sets like the HVM, the V4 and IT data sets, but you can evaluate those using many different measures. You could evaluate them using regression, you could evaluate them using RSA, and then even within regression, you can choose what type of regression you're using. You could be doing something which actually would encourage some sparsity of sampling from the various units of the networks, which maybe actually might be more fair than something like a PLS regression that is typically used. And so each of these methods are going to have their own biases, and it would be very good to know whether things are improving because we're improving them only on one of these metrics versus models are actually improving because they're doing better on all of these metrics for a particular data set.
Okay, Cope.
For me, it will be usability, like user interface. I think we should lock the software engineers in a room and not let them see the light of the day, whereas someone else who actually will be using it as another researcher in this field might be able to communicate what they're doing through the BrainScore website to the community. Because I think at the end, if nobody uses it, and if it's the same 5 people who uses it and we know who they are, it's not really revolutionary for the field. So I think usability and user interface is, for me, the top choice.
Yeah, I think I agree with everything that's been said here. I guess the other obvious one is just including more benchmarks that are just experiments that, of the sort that have been described here. Adding more of those and not aggregating over them, but just studying them individually. That would be great.
Okay, in that spirit and towards Ev's comment too, it's more benchmarks. And as Dan pointed out, and many of you point out, the fuel of BrainScore is the data and the benchmarks, which is, to remind you, is data seen through a metric is what's referred to as a benchmark. And as Janelle or someone pointed out, models are easier to come by, and that, but how to incentivize folks to submit, this is one venue to do that. There's a longer range view that many of us hold that it should be rewarding for scientists, experimentalists, to do an experiment, whether it's hypothesis-driven or not, that disrupts the models, and that was the spirit of this competition. And that should be more important than writing a paper about their data in a way. Is the field that many of us could imagine in the future. And so I'm looking, I see Ev nodding, how do you believe in that dream, and how do we get to switch from an incentive model, which is tell a story about your own data set. You're a grad student, you got to push the monkey around for 2 years and then get some data and then tell a cute story that was hypothesis-driven, or you submit your data set and disrupt all the models that they all suddenly fall to the floor on predicting something that you collected, whether it's behavioral or neural, as wow, that's an important result. I've disrupted the standard model of physics kind of result, right? I've disrupted the standard model of vision is sort of the dream there, or of language. Can we get there, and what do we need to do to make that incentive so that people keep doing experiments for exactly these reasons? Otherwise, there will be no fuel, right? Any thoughts on that? How to incentivize better? This is an attempt, even this meeting.
I have no answers. It's a very hard question. But I just remember when I was a graduate student, I think in my first or second year, Steve Piantadosi, who is now faculty at Berkeley, said, we should just stop writing papers. We should just put up the graphs. Here's our results, and just let the field interpret. And I was like, no. We should not do this. Science is all about storytelling, and there have been many cases where some data have been lying around, and not until somebody comes in with a particular lens, thinking about things in a particular way, that these data become important in the way that they have become important later. And I don't know how, maybe because I work on language, but even though, we've shown that language is separate from thought, but somehow it seems that putting a scientific narrative into a set of clearly articulated arguments, I don't see how numbers would ever replace this, but maybe I'm just a very short-sighted individual.
I agree. I guess I don't see why you couldn't disrupt all of these benchmarks, but then also have your paper in whatever form it is, which explains what you did in order to do that, what the experiments were, what the story is. That seems incredibly important, because the code on BrainScore, we don't know if we're going to be able to run it in 15 years. And so at least having having at least a PDF, which generally explains, maybe not a PDF, I don't know, however you want to store your files, but something.
Just put the graphs into GPT-4.
Yeah.
No, I agree with you.
Yeah, but just something, so that we can actually, as a field, look back on it and say, okay, this is generally what was going on.
I think that we should increase the prize money from 3,000 to like 30,000 maybe. Like it's. I think I actually honestly. So first of all, I think there's already a lot of problems to solve. This is like trying to tell everybody else how to do things, which is nobody's going to like that. So the way to win them over is by increasing the prize money. And I think then slowly, because then slowly the publication strategies might be like, I'll publish one less paper this year, but maybe contribute to BrainScore.
Okay, good. I like your bluntness, Co. Yeah. Jeff, any thoughts on incentives or?
Retrospective sounds like a good plan. No, but the general thing is, I don't think papers should go away. So it's great to have a score and BrainScore, but have a paper associated with each benchmark. And
Okay. There's a little bit of time. If anybody in the audience wants to direct the discussion anyway, please step to the mic and I'll call on you. Otherwise, I can keep asking questions that these guys have been queued up for. So I'm just opening that invitation. Actually, it's 3:45. We have 5 minutes left. Is that right, Martin? 5 minutes or so at most. If any has a question, step up. But it sounds to me that even Jeff, I might say, has started to at least say there should be allowable to have BrainScore as an available platform, maybe ideally fueled by hypothesis-driven experiments that then get incentivized to be posted where papers are also published alongside those things. If I could try to channel your view in a constructive way, given the BrainScore community, is that a fair summary, or have I misspoke?
Yeah, I mean, it just doesn't feel to me doesn't feel like what I imagined BrainScore was. But yeah, if what BrainScore became was a public platform for making it easy to test models on key experiments, then that's and then you don't kind of compete to get an overall score, but it's an opportunity to make it easy to assess your model on a critical experiment. If that's what BrainScore becomes, I'm all for it. Yeah.
Okay, great. Does anybody? And then again, we're going to end in a few minutes here. Does anybody have any parting thoughts of things in this discussion that's prompted for them, or? Yeah. Oh, there is someone there. Okay, go ahead.
Thanks for the great discussion. I think it's very interesting that we kind of like landed on this, multiple scores or multiple aggregate scores not good, because isn't that kind of like, ML scores or like even, original brain scores is one score, right? So, I mean, I'm not 100% sure if this is what Jeff would be pushing, but isn't that against the idea of having the benchmark or a competition at all? If we're trying to say, what's a good model for V1 or IT? I mean, there should be independent experiments, if you like, and an aggregate score might not even make sense anymore. Is that kind of interesting point to discuss?
Yeah, to try to channel that, I guess the question is, where do you guys come down on the aggregate scores? I heard Dan say disband the leaderboard in the aggregate score, but I also know that I hear people saying we should check that everything worked on all the old benchmarks. So there's a question of we can do the aggregation in different ways, but the spirit of the platform is to, let's say, unit test on everything in the past and give scores on everything to push towards models that can explain across domains rather than targeted for single domains, so to speak. But that does sound like an aggregation once you and you need to summarize that.
Yeah.
So how do we balance out the displaying all the scores versus then, combining them to give an answer of the best integrative model, so to speak? What is a strategy on
I think that when the scores are not highly correlated, you shouldn't be aggregating that way because it tends to destroy information. Okay. So if you look at the correlation matrix, score versus score, across the models, and you see, there's some blocks in the diagonal, block diagonals in that matrix. Those can be used essentially to form clusters that you might want to aggregate. But since actually it's the case that we still don't know what those clusters are, I think I would not disband actually the leader, but I would just de-emphasize. For example, in computer vision, they actually don't aggregate that way. What they do is they have several key things where they think these are the things we need to get better at, and they have like little subtracks of the competition. Like, COCO, for instance, has like detection and localization, this and that. Okay, we should do that.
Okay. Any other quick thoughts? And maybe you could take one more quick question from the audience I see, and then we're going to have to wrap up here. And Unless, Janelle, are you burning to say something or no?
Oh, I was going to say what Dan just said.
Okay.
Which is
All right,
Cool.
second that. Okay, go ahead, please.
Thanks for the cool platform. I think one of the most understated benefits of this is having a single API to access a bunch of data sets. So it's very difficult to like go to individual papers, look at how each person has their own idiosyncratic way of packaging their data. So just having access to the data sets in the same format is already a very, very useful tool, even if you don't include the benchmarking at all. And I think improving the usability of the platform and like encouraging people to publish their data sets in the BrainScore format would be a very strong step. I mean, there are already a bunch of existing data sets that just require packaging. It'd be nice to incentivize that as well. Cool. Thank you.
Okay, I'm gonna sort of end on that positive note about data sets. And as you know, there are more mandates from the federal government to post data sets. There are more platforms for data sets, things like Dandy and others. And I know the BrainScore team is working on porting those things so that things flow naturally into platforms like BrainScore in this spirit of open science and access. So thank you for highlighting that point. And I want to close today by first thanking the panel. So let's give a round of applause to all these guys. And again, I want to say the only reason this platform really exists is partly because Martin started it. So I don't know, thank you to Martin and the rest of us are just trying to help keep it going, and I'm glad to see the community growing, and it requires constant community tending and support and in all kinds of ways. So those of you who are interested in contributing to the community, please come up to any of us afterwards, and there's always some ways to help. You got big, deep pockets, that'd be great. We'll pay for engineers. But otherwise, contributing all kinds of other things on the code base is exactly how this makes this thing work. So please come up, especially to Martin and the team here, to talk about those things. I want to thank everybody for attending this event. Martin, did you have anything else you want to say at the end, or am I the end here? Oh, shirts. Yeah, we got swag up here. So thank you guys all for coming, and we'll hang around. Thanks. Okay, bye.
Thank you. Thank you.